Well, we left off around here. Simulation. Simulation. Oh, you can't see what I'm talking about. Let's fix that laptop. I have to plug it in. There we go. Okay, simulation is when, so we talked about modeling and we talked about optimization. So optimization was, we're looking for an input that gives us like the best output. We know the model, like TSP. We know how to calculate the total Euclidean distance. It's easy, you just add numbers together. The output is, well, what was the total distance? And of course, this is just an example. And the input is, well, what configuration? What's the path? What's the Hamiltonian cycle? Modeling, on the other hand, was, okay, it's easy, like the input is known, the output is easy, but I need to do some form of modeling. Like, what the heck should that model be? If it's something simple like calculating the total bill, well, okay, we could just code that up. But sometimes we have hairy issues where it's like, okay, we'll classify these flowers based on lengths and widths of some measurable quantities or measurable features, right? So like, what type of iris is this? Am I really going to sit down and write a billion if statements to measure all the different? No. What I'm going to do, I'm going to use machine learning and hopefully I can find like a good model. Sometimes these modeling problems can be framed as optimization problems, often in like AI machine learning, where you kind of flip it, where you create like the conventional input, model, output, right? But what you do is, well, we're looking for the model. And then we take like a step back and be like, well, the input to our optimization problem is the model is the input. And then our model is like, well, count up the accuracy and the output is the accuracy or something. So it's just how we frame it. Often we don't even think about how we break these things down into how we frame it differently. We just do it. And then finally, we have like simulation. That's where, okay, we have some input, we have some output. Sorry, have some input, have some model. What's the output? And we can simulate certain things. Search problems. This is, given some space, we have to traverse it and find something. If you imagine, we have like we can think of this room, right? Let's talk about the floor, this two-dimensional floor here, all right? I can move along and measure the temperature at any point in this room, in this two-dimensional space. It's three-dimensional, fine, that's three-dimensional space. I'm moving around and I want to find the temperature. And I want to find the hottest point in the room. Right? There will be a point in the room that's like the hottest, let's say. So the search space, it's kind of funny. Like, although the search space is clearly this three-dimensional space, you can also kind of think about it as like a gradient of temperatures, right? Like, I realize this is two-dimensional. So imagine I am traversing this two-dimensional space, okay? This is the room, length and width of the room. And I'm always measuring the temperature immediately off the floor because I'm too lazy to deal with height, all right? We think of the height in this graph, the z dimension is the temperature. And as I move throughout the space, the temperature is going to change, and I want to find the highest point, all right? Now, optimization versus constraint. TSP was an example of optimization. There's a very clear gradient, and given two solutions, they might be equivalent, but one might be better than the other. And how do we know? Well, based on what we care about, the total distance. Sometimes optimization problems can have constraints. For example, maybe if you're doing TSP, maybe you have a situation where don't be late next time. Otherwise, don't show up. The maybe we have a constraint where, well, we have to visit city X before city Y. Why? I don't care. I don't know. It's some constraint. And we have problems that really are just some constraint problems, like n queens. N queens was a situation where just find a valid configuration. If I have two valid configurations and you ask the question, well, which one's better? That's probably going to be hard to answer, right? Because, like, well, they're both valid. What do you mean better? Now, if you had two configurations where one configuration had no conflicting queens and another configuration had one pair of conflicting queens, and another configuration, let's say we had a third, another configuration had two pairs of conflicting queens, or maybe just three conflicting queens, where they could attack each other. Well, yeah, there's a gradient there. The one with no conflicts is better than the one with one, which is better than the one with two or three or whatever. So sometimes you can kind of think of these constraint problems as optimization problems, kind of. Hopefully you see what I mean, where two valid configurations where there's no conflicts. Well, what's better? It is what it is. There's no conflicts. But if you have a configuration which really isn't a valid configuration, but it's better than others in the sense that it has fewer conflicting queens, well, that's a good thing. I realize a lot of this is abstract, and until we have concrete examples in front of us to tease and tinker with, it's hard to kind of get a sense of what I mean, but anyways, am I recording? Good, I am. All right, hardness. Well, who has taken theory of computing yet? Has anyone here taken third year algorithms? Maybe you've taken that, yeah? Did you talk about hardness in it? A little bit, okay, yeah. So hardness. Well, it turns out there is like a scale of difficulty of problems. And I don't just mean, all right, next time, for real, next time, don't be late. Or next time you're this late, I'm telling you to leave. That's it. I'm not just saying like, oh, one TSP problem is harder than another TSP problem. Yeah, sure, okay, it could be more difficult, let's say. But there really is a well-defined metric of hardness. And I'm not going to get into the details there because that's outside the scope of this course and it can be rather complex. But there are some problems out there that are just so goddamn hard that, well, we don't really have good solutions for them. And there are other problems that might seem hard, but we have a nice strategy for solving these problems. For simplicity, a problem is easy if there is a fast solver for it. And when I say fast, I mean it's an algorithm that can run in like polynomial time. For those of you that don't remember, polynomial time is, it doesn't need to be linear time. It doesn't need to necessarily be like n squared, like big O of n squared. It doesn't even necessarily need to be that. It could be like n cubed or whatever. But it is polynomial time. Like we're not talking about something that's like n factorial, big O of n factorial, big O of 2 to the n, something that's exponential. That's where we have problems. And a hard problem is one where, yeah, we got no way to solve it. So if we go back to TSP, we saw that it's like big O of n factorial, right? How many combinations of, I mean, we want to get specific. We knew, well, it's the number of cities minus 1 factorial divided by 2. Fine. But it's on the order of n factorial. That's the problem. We don't have a good way to solve it. There's no fast solver. Now we have continuous versus discrete spaces. Well, if we have a problem that's defined in terms of like real numbers, continuous numbers, we call it like numerical optimization. And these problems have uncountably infinite search spaces. Did I talk about like the infinities yet? How there's actually different types of infinity? Just to remind you, if we're talking about like natural numbers or integers, if I say what comes after 1, what do you say? 2. What comes after 2? 3, 4, 5. And we can play this game forever towards infinity, right? Now if we're talking about real numbers, numbers that have decimals, and I ask you what comes after 1, what do you say? Yeah, keep going. Yeah, we got a problem. Because as soon as you pick a number, I go, but there's one before that that comes between the two. And then as soon as you pick one of those, I could do that again. We could play that game forever. So not only with like real numbers, with continuous spaces, we have infinity that goes on towards like infinity, but we also have like an infinity between each goddamn number there is, which is crazy. Where when you have discrete spaces like integers, well, we could just go towards infinity. It's weird to say, but like integers, okay, natural numbers, 1, 2, 3, 4, that goes on forever, right? And integers, which is the same, but we also have negative numbers. You want to hear something weird? There's the same number of numbers. And you're gonna say like, well, like intuitively, there's like twice as many integers. No, there's not. It's the same. Which is weird, but you know, but as soon as we talk about like continuous numbers, yeah, we got a problem. They're quite clearly not the same number of numbers because we can't like put our finger on each of them. Okay, problems are defined in terms of discrete values like integers, then it's called combinatorial optimization. These problems have finite or countably infinite search spaces. So you might have a situation where there really is, like with TSP, if I give you 100 cities, yeah, there's a lot of combinations, but there is a finite number of them. There is. But there are other situations where there might not be a finite number. There might be an infinite number of possible solutions, but it's less bad than continuous ones. So what to know about hardness? Well, we have class P. These are decision problems that can be solved in polynomial time. When I say polynomial time, I mean something that's like n squared, n cubed, whatever. Like it could get bad, but it's not that bad. Then we have class NP, and these are decision problems with positive solutions that can be verified in polynomial time. A solution where, sure, it might be really hard to find a solution, but you can give it to me and I can confirm its correctness in polynomial time. And then we have NP-complete problems. Oh, here we go. Okay, for example, restricted subset sum. Does there exist a subset of a set of integers that sums to 0? Okay, so this is actually a very challenging problem. Basically, if I give you a set of number, any arbitrary set of numbers, and I ask you the question, can you add some subset of them such that the sum is 0? Right? So maybe I give you the number like -10 and 10. Well, that's easy. You add them together, it's 0, right? Now, the choice of 0 is arbitrary. It could be any integer. It really doesn't matter, but, you know, that's subset sum. Now, when you have large sets, this becomes quite challenging. But if you give me a solution, I can confirm its correctness easy. You just add up the numbers. Does it add to 0? Yay. But finding a solution is hard. But confirming its correctness is easy. Then you have NP-complete. These are decision problems with no known polynomial algorithm, but can be verified in polynomial time. So we can confirm. I was being a little bad here. I was really talking more about this here, NP-complete. I don't know if there exists, and we're very careful in computer science to say, it's not that there isn't a polynomial time algorithm, it's that we don't really know if there is one. Maybe there is one, maybe someone just hasn't discovered it yet. But maybe we can do it. But we can confirm it in polynomial time, and all NP-complete problems are actually reducible to one another, which is a fancy way of saying there is a classification of problem called NP-complete, and there's a lot of problems that are NP-complete. But as it turns out, all of those problems, although they seem different, they're actually all effectively slightly different formulations of the exact same problem, which is interesting. And then finally, we have NP-hard problems. These are decision problems with no known polynomial time algorithm, and we can't verify its correctness in polynomial time either. So these ones are like, well, we're screwed. Anyways, we're not going to be too worried about this. So after all that, that really is something we could figure out in a whole other class, in like theory of computing and algorithm analysis, like 30 algorithms, 355, 356. But what do we really need to know about hardness? Well, sometimes there's some pretty goddamn hard problems out there. And often with these types of problems, because we concede the fact that, look, I don't know how to find a good solution to this problem. Like, I can't solve this problem in polynomial time. Maybe someone else can. Maybe someone will invent it and they'll become a bajillionaire. And they'll break the world if they do it. But we can use AI, optimization, machine learning to find good enough solutions to these problems that, whatever, they solve the problem good enough. If I own a logistics delivery company and my delivery people don't need to go visit 100 places a day, great. I'm exceptionally unlikely to go find the best solution, like the best order to visit people to do my deliveries. So I'm just happily going to go and accept something that's just sufficiently good. And that's fine for me. And these are where things like evolutionary algorithms come in, and other forms of computational intelligence. Any questions about any of that? Cool. Now this is just to give you a sense of the problems. What am I doing here? All right. All right, some of the origin. Now, I'm going to warn you, some of this stuff is fairly loose. Okay, the computer scientists borrowed a lot of words and ideas in a less than accurate way. It's sufficient for us to wrap our heads around things, but if is anyone in here a biologist? Then we're safe. But if there were, they'd probably be angry about the stuff I'm about to say because I'm going to be loosey-goosey, all right? So evolutionary computation is inspired by the natural process of evolution. However, we use a lot of jargon from biological evolution. It's important to not focus too much on living organisms because if you do, you're going to get lost in the weeds. This is more of an abstract comparison. So at the end of the day, you know, we've got these like phylogenetic trees, which is basically like if you go through and you kind of take every living thing and you find all their common ancestors and you go back, you like imagine every living thing on the planet, and if you go back in time, they're all going to start to converge to some point where they all kind of came from something. Probably, maybe not, who the hell knows, but let's say. And they have got this thing called like the last universal common ancestor, LUCA they call it, all right? And so we've got like animals, bacteria, I don't even know what this is, archaea, I don't know, what is that? Bacteria is bacteria, eukaryota, that's like us. Apparently slime molds too. We're related to slime molds, great. And I don't know what this is. I don't know. Someone look up what archaea is. But the point is, the power of biological evolution is quite clearly evident in the world around us. I mean, look at the diversity of living things on the planet, right? So clearly, there's something there. And you figure, like, you look at me, and then you look at a groundhog. Well, a groundhog is a hell of a lot better at digging underground than I am, right? I need a bunch of tools to do it. The point is, we're different, and we end up having different skills, and it's interesting. So what's also interesting here is it's very, maybe difficult isn't the right word. So on this topic, you're going to have to go with me and try to take a couple steps back and think about the bigger picture and ideas, all right? Obviously, there is a difference between like a living thing and its environment, right? I am obviously a separate entity from this space right now, obviously. However, when you take a couple steps back, can you really like distill humans from their environment? Like we are a product of our environments. I don't mean like, oh, you from being a baby to this. I mean like, no, like the species. We exist the way we are because we exist in an environment. And the environment has an effect on us, whether we like it or not. In fact, we kind of are a part of our environment. Because as far as I'm concerned, you exist in my environment. Like, how can I differentiate you from my environment? You are a part of the environment. It's kind of weird. And it's kind of weird too, because this is, like, warning, humans have this insatiable need to categorize things and separate things and put everything in a box, when reality kind of is not conducive of doing that. Things are far too fuzzy and hairy to really be able to do that. So we're obsessed with categorizing things. And as soon as you start looking at like things that we've created to categorize things, there's 1,001 exceptions to every category because, yeah, is it really even valid in the first place? So environments are filled with populations of individuals that strive to persist. It's not that it's not even necessarily that an individual has this strive to exist. I have this innate desire to continue to exist, okay? I do things like eat. I do things like try not to die, right? Like these are things that like obviously I do, but again, think of a population, not an individual. Like think of like the human species. The human species has like built-in mechanics, and not just humans, I mean like every living thing, has built-in mechanics, whether like these things have whether, like our mice are some arbitrarily insignificant little living thing that has an ability to reproduce. It's never thinking to itself, I need to reproduce for the survival of the species because this is important for whatever. No, of course not. That's ridiculous. No, they just have these like mechanisms and things that they follow that cause this to happen. If they didn't, they wouldn't be here. Okay? This is where things gets kind of like, it almost sounds like I'm trying to be like in high school and deep. Like, oh, I'm so reflective. But trust, like that's really not what I'm trying to do here. I can look at this table. It's like a survivorship bias type thing. I can look at this table and be like, oh, why is this table here? Well, this table is here because blah, blah. Like I can come up with all these explanations, but if that table wasn't here, we wouldn't be talking about it. Do you kind of get the point I'm making? Why is there not why do we have two arms? Because we don't have one. That's, there we go, right? And we don't have three. If I had one arm, think of another timeline where humans only have one arm on average, right? We'd be saying, whoa, why don't I have two arms? Ha 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 ha. It's because we don't. And a species that exists, that has existed for millennia, since who the hell knows how long, why does it exist? Well, if it didn't exist, we wouldn't be talking about it. It's hard to tell you what I mean. Systems are like we only talk about systems that exist. If they didn't, let's say, out of nowhere, some omnipotent deity shows up and creates a little, I don't know, remember house hippos? Remember house hippos? Let's say, boom, house hippo. Great, they create one house hippo. And we're like, oh my God, it's so cute, right? It's running around. Okay, so for those of you that don't know, sorry, I realize half the room are international students that probably have no idea what the hell a house hippo is. Yeah, this is probably, I mean, hell, it's probably from before your time. North American house hippo. It was this like joke. I'm pretty sure it was a Canadian thing. Yeah. Okay, the North American house hippo. The house hippo is a fictitious species of hippopotamus and the subject of a Canadian television public service announcement produced by concerned children's advertisers, later known as companies committed to kids, in May 99 and reintroduced by smart kids in 2019. Oh, I didn't realize it came back. Cute. So house hippos, it was this little ad on TV. And the point of this ad was to raise awareness about bullshit, basically. All right? Like, hey, this is nonsense. Like, we have to, be aware of this stuff. And the idea was there was this little house hippo, and it was just this little, fake little hippo that would run around houses, kind of like a rodent, like some pest that you wouldn't want or something, okay? A house hippo. So now that my example has been explained, it's obviously nonsense. There's no little hippos running around. If this deity that showed up and created a house hippo only made one, and that one had no ability to asexually reproduce, eventually it will die, and no one will talk about it ever again, except for people like, hey, remember that time there was an actual house hippo? Oh, that was wild. But it would die out because it had no ability to reproduce. It had no ability to persist. So 1,000 years from now, no one would talk about it. No one would care about it. Why? Because it doesn't exist. It didn't have the mechanics to persist. We, as humans, have we have a built-in ability to persist as a species, right? We try to stay alive, and we produce offspring that carry on, and so 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 on. We only talk about these things because they exist. Hopefully you get the point I'm making. Yeah, so the populations of individuals that strive to persistence through survival and reproduction. The fitness of an individual is a measure of its ability to persist. Things that are more fit have a better ability to persist. We could talk about fitness in terms of a species or an individual, right? The fitness is determined by an individual's interactions with the environment and other individuals. But again, like I was saying, other individuals are effectively a part of the environment. With evolutionary computation, populations of candidate solutions are evolved. The fitness of the candidate solution is a measure of how good it is. It's a goodness measurement. Now, it's funny because with evolutionary computation, we design our environment. What does it mean to be good for a candidate solution? Where us, we just exist in our environment. And what does it mean to be good in our environment? Well, we don't really have a say over that. Just our environment sets that. Okay? But in evolutionary computation, we can flip it because we get to design the environment to say, well, what's fit and what's not. And the candidate solution's fitness dictates its probability of survival and reproduction. Cool. Any questions so far about any of that rant? Whoops. So diversity. Reproduction creates imperfect copies of individuals. This is the way it is. We can talk about things as if literally asexual reproduction within my cells. They can reproduce. They don't need anything fancy. There are inaccuracies that happen all the time, but also in species more at a higher level. Sexual reproduction, which is fascinating, incorporates genetic information from both parents. So it's not even really possible to make a perfect copy. And mutations happen both in sexual and asexual reproduction all the time. So the point is we make copies, but the copies are different. They're never perfect. Sometimes these changes are harmful, and that's the way it is. If a living thing had a mutation that made it unable to digest food, well, it's not going to last very long, is it? Some changes are neutral, benign, have no real impact. Maybe after something, maybe some people have slightly longer legs than other people. Doesn't really matter. It doesn't, okay, cool, neat. And sometimes it's beneficial. Maybe having slightly longer legs makes it so you can run away from lions faster, so you survive better, right? So sometimes it can be beneficial. It's hard to say, it's weird. And what's interesting is we get a lot more negative changes and benign changes. So while we get a lot of benign, neutral changes, Negative changes will obviously die out fast, but good changes can take a long time to take over a population. So if you have a population where they have a mutation that is negative, they will die out fast and not persist anymore. A population where they start to have a good change, well, it might actually take a long time for that good mutation to take over. But bad mutations, well, they tend to die out really quickly. Good mutations tend to take a while to really matter, which is kind of interesting. And when you think about it, if bad mutations die off fast, then bad mutations have a less likely chance to persist, which is kind of a good thing for a population. Like if I made a change to a TSP configuration that made it way worse, well, we don't want those things to persist in the population. Have that die off quick. But the point here is when we're making when we are reproducing and creating new copies of like our candidate solutions or anything, the imperfectness creates diversity, and that's a good thing though, in general. And competition is kind of like the flip side of the diversity. Not necessarily, but we can kind of think of it like that. Given that environments have limited resources and individuals have an intrinsic interest to persist, competition and selection becomes inevitable. It's going to have to happen. There is only, how many computers in this room? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say it's 10 in each row. So 10, 20, 30, 40, 50. Right? If 60 people showed up here and they each needed a computer, people are going to have to like rush to get to a computer. It's going to happen, whether you like it or not, because there's a limited resource. That's it. It's the way it is. Tough. So it's necessarily going to happen, whether we like it or not. And if someone shows up and, I don't know, they forgot their glasses and they really need glasses and they can't see where the computers are, well, chances are they're probably not going to get to a computer as fast as someone who can, oh, there, I got to go, run, right? Bad example, but you probably get my point. That was a really contrived, silly example, but you probably get my point. Okay, so individual versus population. It's important, like obviously we are aware at the individual level when we're talking about candidate solutions. But it's important to think of like, okay, individuals are impacted by all these mechanics. But it's important to think of the populations, because the populations are evolving. And we even saw that when we were doing the bit string thing, right? And we plotted the average population fitness. What happened to the average population fitness over time? It got better. The best candidate solution hopefully got better too, but the whole population fitness got better over time too. The populations are evolving. And it's often helpful to think of populations evolving instead of the individuals themselves. And having a balance of competition and diversity is very important for populations in the long term. In evolutionary computation, a balance, like two of the key driving forces, competition and diversity. These are two very important forces. And sometimes these things are in conflict with one another. Whether we like it or not, they are within our search, with our search algorithms, okay? And this is where you start to talk about like exploration and exploitation, right? Exploit what's good and explore differentness. We have to strike a good balance between these two things. And that's where a lot of these like hyperparameters come in, is it's tuning these things to the right spot such that we don't want to converge too quickly and we don't want to have too little competition such that the search never really has a chance to converge, right? It just kind of like flounders about. We have to balance these things together. All right, systems. Okay, populations of living things evolve. But a population of living things is just a system. And a system exists within some environment, which itself is a system. And the population is made up of individuals, which themselves are systems. And each individual is made up of many more systems, and each of those smaller systems is made up of other systems, and so on 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 and so on, right? So it's weird because all of these ideas I'm talking about, we can talk about at the level of like individuals, we could talk about it at the level of populations, we could talk about it at the level of systems within an individual. We can talk about it in terms of several populations within a larger environment, right? Like I'm competing for food with dogs too, I guess, right? Like there are so many levels and layers to this thing. We can play this game forever and ever and ever and ever and ever. We can play this game down to how particles interact with one another, right? Why do they interact that way? Because they do. Why did we evolve the way we did? Because we did. And if they didn't act that way and they didn't evolve that way, it wouldn't work the way it does. So it's the way it is. Systems can evolve, not just biological systems. This is an important thing. This is a very important thing. A lot of people don't take the time to really think about this. Don't put life on a pedestal. It's just another system within our universe. It really, like, all we really need is a mechanism for persisting and changing. Systems evolve as a consequence of its relationship to its environment, whether it's alive or not. That's it. Sometimes the environment has some intention behind it, and sometimes it's aimless. If we are creating the environment for TSP, or our genetic algorithm for TSP, yeah, we're putting there's method to the madness. And sometimes it's just us floating around in our universe, which why? Oh, because, right? Like it happened that way. Cellular automata. Anyone know what this is? You might be more familiar with the next thing, but let's go on with this. So, an elementary cellular automata is a very simple system of rules, okay? Very simple. Given a one-dimensional linear sequence of binary values, zeros or ones, I'm going to represent these zeros or ones as little cells. If there's a box in it, we got a 1. If there's nothing in it, it's a 0. Or vice versa. It doesn't really matter how you implement it, but that's the idea. We create okay, cool? That's the starting position. Why do I have this? It's just some arbitrary string of zeros and ones. This is rule 30. Why is it rule 30? Well, this is the binary. If you were to take this out, I guess this would be, I can't remember. I'm sure I explain it. Give me a moment. This is rule 30. So we have a one dimension. How many do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 30. Okay, I've got 30. I don't think that's why it's rule 30 though. Maybe it is. I don't know. We've got 30 cells. And the cell has something in it or not. Cool? Do we understand? So here's what we're going to do. Is we're going to create the sequence's next generation based on the cell's current state and the state of its neighbors. All right? So I'm going to look at like a 3-cell window. Okay? And depending on what I see in that 3-cell window, I'm going to produce some output. Just go with me on this. So, here's rule 30. Okay, this is what it is. Starting condition, rule 30. Why is it rule 30? Well, if you take the binary representation of what this is, you get the number 30. 0, 1, 1, 1, 1, 1, 0, 0, 0, right? That's what that is, okay? Cool? If I see 3 ones, I produce a 0. If I see 1, 1, 0, I produce a 0. 1, 0, 1, I produce a 0. 1, 0, 0, I produce a 1. 0, 1, 1, I produce a 1, and so on and so on and so on. Cool? So far, so good? It's a simple little game. So based on this, I would see 1, 1, 0. So I see 1, 1, 0, I produce a 0. I would move to the next one. Okay, hold on. See, here we go, right? See how it's going? Right? Cool? You follow? Nothing crazy. Simple little system of rules. Exceptionally simple system of rules. Let's think about the complexity in which we could define some system. This has got to be at the bottom of the list in terms of complexity. We've just got like a linear thing, and based on what we see, we produce some output. Okay? That's it. Exceptionally simple, right? Hilariously simple, like almost like stupid simple. I could give this to my 4-year-old, he could do this, no problem. Follow these rules, produce this. The hardest part will be him to focus, not his ability to do it, because it's so simple, right? I cannot stress how simple this is. So since each cell's value is determined by 3 cells' previous state, there's a total of 8 patterns since, okay, each of the 8 patterns produces 0 or 1, meaning there's actually a total of different, how many do we have here? 8 potential patterns. 2 to the 8, 256. There's a total of 256 different patterns that we could come up with, 256 different rules, for example. And this is just one of them, Rule 30, right? Rule 0 is really boring because it would just be no matter what you see, produce a 0. Okay, not that interesting. But Rule 30, clearly we're getting something interesting. And what we could do is we could repeat this process. Okay, once I follow that one, I just start again, but on the next generation. Cool? Okay, the above rules, Rule 30 because of it, yeah, whatever. By repeatedly applying these very simple rules to each new sequence, interesting and complex patterns can emerge. So this is an example of Rule 22. If I start with a single point, one single point, and I follow Rule 22, and I hit go, this is the pattern it generates. Now that's interesting. The rule and system is as simple as it gets. It's hard to define a system simpler than this. But if you apply Rule 22, very simple rules, hilariously simple, easy to understand, trivial, you get a very interesting pattern. At least I think that's interesting. Right? In fact, if you were to let this run forever, you would have that like fractal pattern, right? Where you could keep like zooming in and zooming out and you're just going to see the same pattern over and over at every, not only is it going to go on forever, wait for it, if you scale out, so not only does it go on forever this way, as you scale out and scale in, the pattern repeats as well. It's wild. It's crazy. Do you see what I mean? The pattern repeats forever this way, and if you zoom out, the pattern repeats forever like, you know what, like, it's hard for me to know if you get what I mean. It carries on forever this way, and if I were to start like, okay, like forever, right, yeah, and imagine it goes on forever, and I were to stand in front of it, and I didn't have a shadow, and I were to walk backwards, I'm going to scale out, and if I keep doing this, that pattern is going to repeat over and over and over this way as well as I'm observing it as it scales out. Which is wild. With such a simple little rule. If I were to show you Rule 0, that wouldn't be interesting. We wouldn't talk about it. Who cares? But Rule 22, that's interesting because it produces something interesting. We're talking about it. So we care. So here's what I want you to do for the next 5 minutes. Go to Wolfram Alpha. Here's a link. Okay, the link above is a result of running Rule 0. Rule 0. There, that's what you get. Was that fun? Not really. If I go Rule 22, well, yeah, we start to see the interesting patterns. Now it's actually kind of showing you what happens given, so this is the pattern you get if you have the starting string of 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, right? This is it showing you, well, okay, from a random initial condition. I'm actually curious, if I rerun this, does it give you a different random or is it always the same? Looks different, right? Like look at these right here. and hit refresh. Maybe not. Maybe it is the same. It's hard to say. More steps? Well, I think it's just going to, yeah, I don't know. More steps. Fewer, oh, come on, keep going. Anyways. That's interesting. I think it's interesting. So if you go to Wolfram Alpha, rule 20, I don't know. Okay, that's kind of fun. We'll just do that. Oh, neat. Rule 1. That's probably going to be pretty boring. Actually, not too bad. It creates a funny little like pattern. Neat. What was rule 30? It's kind of neat, right? I mean, we could play this 255. Well, it's kind of boring. No matter what, produce a 1. All right. 211. All right. It's like the inverse of 1 or whatever it was, right? Like, cool. Neat. Now, what's kind of crazy is like these patterns arise in nature, which is really neat. So take the time to generate a few patterns, a few dozen if you want. Take note of the interesting ones. And what patterns are interesting? Well, you know, I thought rule 22 was interesting. Rule 30 was interesting. I thought it was really interesting. Now, what's really interesting about rule 30, I hope I'm right. I hope it's rule 30 and not another one. If it's not rule 30, it's another similar one. I'm certain I talk about this a little later, so I'm not going to bring it up. I'm not going to spoil the fun yet. Know what Conway's game of life is? Come on. I'm certain you're aware of it, but you never really talked about it in too much detail. So Conway's game of life is like this cellular automata, okay? It's just like that, but it's in 2 dimensions. I know the cellular automata looked like it was in 2 dimensions, but really all it was in 1 dimension, and we just made it look like 2 dimensions by repeating like each phase in a line. But really what we could do is show that line, just replace the previous line, and we would just see like wild patterns happen, right? Conway's game of life is the same idea, but in 2 dimensions. Instead of comparing a single cell and its neighbors, well, you compare a single cell and its neighbors, but now there's more neighbors because there's up and down and left and right. Okay? That's Conway's game of life. And the specific rules for Conway's game of life and his formulation is any cell with fewer than 2 live neighbors dies off. Any cell with 2 or 3 live neighbors survives. And any cell with more than 3 live neighbors dies off. Any dead cell with exactly 3 live neighbors becomes alive. That's Conway's game of life. Hilariously simple little rules, okay? And with these hilariously simple little rules, we can hit play and simulate this. The blue is showing, I don't know, light baby blue is just kind of showing, and it looks like it fades over time. Will this ever end? You want to know the correct answer? Like, will this ever become stable or metastable? Let's see what happens. So this would be stable right here. This part, it's stable, it's not changing. Metastable would be a situation, there was just one there real quick. Oh, come on. This right here, see? Shit, it died. There, oh, no. So that's stable. And, oh, well, look at that. Will this ever end? Oh, there, that's, oh, no. Those are called spinners. There's one right there. Oh. Step, no. That. They keep, there's one. Oh. The spinners, if you ever end up with exactly 3 in a row, what will happen is each generation, it just goes like that. It just kind of like, it spins, right? It'll go 3 up, and then 3 this, 3 this, 3 this, 3 this, 3 this, over and over and over. There's one. Oh, and it died. It's metastable, meaning if it's left alone, it doesn't change, it just keeps doing its thing. So this is stable in the sense that it's not changing, and metastable is sure it's changing, but it's not. When I ask the question, does this ever end? The answer is, you want to know what the correct answer is? I don't know. That's the correct answer. You'll never know, given the initial conditions, if it'll ever become stable or metastable. We're going to pick up here next time.